Okay, so starting the recording. All right, so once again in section 4.1, you learned about vector spaces and subspaces. So, of course, well, a big part of section 4.1 was identifying when you had a subspace of a vector space, and the subspace itself is a vector space. Because it would follow the conditions of a vector space, but there are only three conditions that you would need to formally prove. And of course, if you have the span of a set of vectors, then any space that can be expressed as a span of a collection of vectors would be a subspace. So it's very helpful if we can identify a space. If we can take a space and express it as a span of some vectors, then that's great, because then we have a subspace, and a subspace is really, we want to have a subspace. The other spaces are kind of strange, you know, when you don't have a formal subspace. So in applications here of linear algebra, okay, they mention right here that subspaces arise in one of two ways. One is a set of all solutions to a system of homogeneous linear equations, or as a set of all linear combinations of a certain specified set of vectors. So let's go ahead here and go right into a few examples here. Okay. And they mention as you will soon discover, we have been working with subspaces ever since section 1.3. Okay, you just didn't really know it, but you probably felt it. But all right, well let's take a look here at this idea of a null space. So the null space of a matrix. Okay, so if you have a system of equations, okay, here they have two equations, and you write that, of course, as the matrix equation A times X equals the zero vector, where A is the set of the coefficients. Okay, then the vector X that satisfies that system is a solution set of the system. Okay, nothing strange here. And we would call that set X that satisfies this matrix equation, we would call that the null space of the matrix A. Okay, so the set of vectors that satisfy the matrix equation AX equals the zero vector, which corresponds to the solution set of a homogeneous system of equations. Okay, that set of vectors that satisfies that homogeneous system of equations, that set of solutions is the null space of the matrix. The null space of the matrix. And actually I guess they have the definition right below here, right? This is really what I just had said. So the null of A, which is an abbreviation for the null space of A, is a set of all X such that X is in n-dimensional space, and it would be if you had an m by n matrix A. Then if you multiply A times a vector X, the dimensions on X would have to be n by 1. So the null space of A would have to be the set of vectors such that X is in n-dimensional space, and A times X equals 0. All right, and they have a little picture here. They have a little picture where, in figure 1, where they have n-dimensional space, and in n-dimensional space, they have a null space there, which is, they're just representing it with a line, but basically they're saying that the null space is not all of n-dimensional space. Okay, it's not the whole, it's not all of the vectors in n-dimensional space. It's just the vectors that get mapped to the zero vector. And you can see that in figure 1. The vectors that lie in the null space of A, all of them get mapped to the zero vector. And the zero vector it's a vector in m-dimensional space. And that makes sense because you're multiplying the vector x by an m by n matrix. So the product would be an m by 1. And so the zero vector would be m by 1. Now, let me ask you in figure 1, why I noticed that the zero vector is in the null space of A. I mean, the zero vector is right there in the null space of A on the left in figure 1. So why would the zero vector be automatically in the null space of the matrix A? That's right, Benjamin. That's right. The matrix A times the zero vector will equal the zero. Well, the matrix A times the zero vector will give you a zero vector. Okay, and so the zero vector is automatically in the null space of A. All right. Are there any questions? And of course, the question is what are the other vectors? What are the other vectors that are in the null space of A? Okay, well, we have to find those. So they start off here with an example where they reinforce the definition. They say let A be the matrix in 2 above. Okay, so that is that's this matrix here, this 2 by 3 matrix. And let the vector u equal this, hold on here, equal this vector here. Determine if u belongs in the null space of A. Is u in the null space of A? Well, of course, what you have to do is you have to take the matrix A times the vector u. And when you do that, you do the multiplication, you get the 0, 0, you get the zero vector. Therefore, u is in the null space. Okay, the vector u is in the null space. Okay, so are there any questions so far? All right, well then let's continue on. Let's continue on. So, all right, they're saying in theorem 2 that the null space of a matrix A, okay, is a subspace of Rn. Okay, it's a subspace. So they're saying that the null space is a subspace of Rn space, n-dimensional space. Let's look at the proof on that. So okay, so automatically it's important, right? If we've identified a subspace of n-dimensional space, that then that's important, right? So why is this true? Well, okay, in the proof we have to verify the 3 conditions. If we're going to prove that the null space of the matrix A is a subspace then we have to prove the three conditions for a space to be a subspace. First of all, the zero vector is automatically in the null space of A. Okay, automatically. And that, remember, for subspace, the first condition is that the zero vector is in your space, and the zero vector is. Now next, they let u and v be any two vectors in the null space of A. And if we do that, then of course, by definition of a null space, that means A times u would have to equal the zero vector, and A times v would have to equal the zero vector. Well, all right. Let's see if the null space is closed under vector addition. That's the second condition we need to verify for a subspace. Well, here's u plus v. If you multiply a times u plus v, you're going to get au plus av, and that's going to equal then 0 plus 0. Hence, you have the zero vector. So that means that any two vectors in the null space, if you add those vectors together, they will also be in the null space. So the null space is closed under vector addition. All right, are there we've proven two of the conditions for the null space to be a subspace. Are there any questions so far? All right. All right. Well, then let us continue a little more here. Last condition is to show that the null space is closed under multiplication by scalars. All right. Well, here's a scalar times the vector u, and a times u equals 0, so u's in the null space. But by the properties of matrices, we can factor out the constant there, that scalar c, and then we get the zero vector. So therefore, c times u is in the null space of A, and that means that then the third condition is satisfied. So therefore, the null space of A is a subspace of Rn. It's a subspace, and it's a special space. Okay, are there any questions so far? All right, well, let's continue on here. So these are simple examples. In example 2, they say let H be the set of all vectors in R4 whose coordinates satisfy these two equations. Okay, so the vectors satisfy those two equations. A minus 2b plus 5c equals d, and c minus a equals b. Show that H is a subspace of R4. Well, all right, what we can do is we can rewrite these two equations as we have them here, where on the right-hand side we have zeros. Okay, and this means then that H has to be a subspace of R4. Okay, because the coordinates of the vectors, well, let me see here. I want to say this the right way. One moment. Okay, think of it like this. Let me go to the so they're sort of leaving out a little step here, but let me go to the whiteboard, and show you an extra step that I think will help you feel comfortable here. Let me go to the whiteboard. All right, and I think I'm going to try, one moment here. Let me see here. Let me try my my little device here. Hold on, class. Oh, okay, it was plugged in. Hold on. All right. Okay, so okay, we had A minus 2B plus 5C minus D equals 0. And then we had negative A minus B plus C equals 0. So we have these vectors these vectors that are in R4. Okay, maybe I don't want that there. We have these vectors A, B, with components A, B, C, D that we showed satisfy this system of equations. Okay, and what we can do, you see, is this system, we can write it like this. Okay. All right, so this is A, this is X. The dimensions of A are what? The matrix. It is a 2 by 4. So naturally X is a 4 by 1. How many components in the 0 vector? Good, good. 2, because we are taking a 2 by 4 and multiplying it by a 4 by 1 vector. Okay, so this has to be 2 by 1. And so you see what you're doing is, you learn that you can take any augmented, any system of equations and represent that system as a vector equation. But the point is that based on this, then the vector x is, hold on, one moment here. I want to just say this the right way. So space H, I'll just kind of be nice if I had the book here. I have it, but space H was the set of A, B, C, D such that A minus 2B plus 5C equal D. And then the other restriction was that C minus A equals B. Okay, I mean, if you look at example 2 in section 4.2 of your book, this is how space H was defined. Okay, so space H is the set of vectors, okay, in R4 that satisfy this condition and this condition. Okay, but what we did was we basically then rewrote the conditions this way, and then we expressed the conditions then this way. A times x equals 0. And so that shows then, that H is equal to the null space of the matrix A. Okay? And therefore, this space H is a subspace, okay, of R4. Because, again, because H is equal to the null space of A. So if you can show that a space that you have, this was our space right here, if you can show that it's the null space of a matrix, then that space is a subspace, and it's a subspace of R4. Okay, does that make good sense? Are there any questions on that? Eleanor's good. Okay. Wonderful, wonderful. All right, let me know if you have any questions. All right, so looks like the stylus I'm able to write a little faster, and that's okay. That's all right. May I go back to the book? Are we good so far? All right. All right. Thank you, everyone. All right. I will go back into the book. Okay. So now an explicit description of the null space. Okay. Explicit description. So here in example 3, they want you to find a spanning set for the null space of the matrix. So remember, when you have a subspace, there are vectors that generate the subspace. The subspace is created by a linear combination of those vectors. And so the vectors basically are the foundation of the subspace. So when they say spanning set for the null space of this matrix, that's what they mean. Well, of course, what we have to do is we have to solve this augmented matrix. Okay, you have to solve this set of equations, this homogeneous system. And well, what they do is they leave out the step here, but they do row reduction. They have, you know, I mean, think about setting up the the matrix equation A times X equals, the matrix equation A times X equals 0. You write that as an augmented matrix. You do row operations on it. And what you're going to end up with, is this here. Okay, you're going to end up with, no, hold on. You're going to end up with this augmented matrix in reduced echelon form. Okay, and so again, the row operations are not hard for the smaller problems, and certainly for your next exam, I'll want to see row operations, and I'll let you know when when MATLAB is fine, but certainly for harder problems we use MATLAB. This is no big deal. All right, in order to find then the spanning set for the null space of matrix A, we need to talk about the solution of the matrix equation AX equals 0. So, okay, well, let me ask you, based on what you see here on the bottom right, 2 equations, 5 variables, and the 2 equations are not the same. How many, well, let me ask you, how many vectors, well, first of all, the null space lives in what space? Would it be R3? Would it be R4? Would it be R5? Where would the null space live for this matrix A? It would be, and I appreciate all responses, it would be R5. It would be R5. Hold on here. Good hung, and so the matrix A is what you're. So here's the thing. What if I'm gonna? I mean, if I'm multiplying. Let me just kind of take off some of the stuff here. If I'm multiplying A times X here, okay, and the vectors X that solve that homogeneous system of equations, those solution vectors X generate my null space. Well, in order for matrix multiplication to be defined, A times the vector X, A is what are the dimensions on A? No problem, no problem. Yeah, that very good, Benjamin. Thank you. The matrix A is a 3 by 5 matrix. Okay, and so the vector X would have to be a what? If A is 3 by 5, then the vector X would be what? Then the vector X would be, well, so hold on here. Hold on. Here's A times X. Okay, and it's going to equal the 0 vector. A is 3 by 5. Okay, so what would the dimensions have to be on vector X for that matrix multiplication to be defined on the left? Phi by 1. Okay, and so therefore the null space for the matrix A lives in R5. It lives in R5. Okay, are there any questions on that? All right, let me go back to the example then. Okay, so, but how many vectors are going to generate? All right, so we know the null space. Who's comfortable that the null space is in R5, in 5-dimensional space? The null space is a subspace of 5-dimensional space. Is everybody comfortable with that? Okay, good, good, good. Well, my next question is, how many vectors are going to be needed? How many vectors are going to generate this null space? Based on that system of equations on the bottom right. Okay, and I appreciate all answers. I'm getting a lot of answers. Unfortunately, none of them are quite right, but I appreciate it. All right. Haley, that's right. 3. Why? So again, I appreciate answers, participation, and it's fine if you chat out an answer and it's not right. You're learning, and sometimes it's good to how many find when you participate and maybe you share an answer, okay, and it's not right, and then you see what the right answer is. How many feel that helps them really learn, even if they participated and it wasn't the right answer? Okay, good, excellent. Well, all right, so Haley thinks 3 vectors are needed to generate this null space. Okay, and Benjamin agrees. And so the key is we have to express the solution vector in parametric form. I mean, the solution vector x is going to be in the null space of the matrix A. But let's express that vector. Let's express it. So okay, all right. So well, the general solution, if we hold on here, based on the system of equations, the reduced system of equations on the bottom right, what are your free variables? What are your free variables? How many free variables are there? 3 free variables. And what do you want them to be? We have x1, x2, x3, x4, x5. What are you going to let be your free variables? Which 3? Nafani, I agree with you all. X4 and x5. How about x3? Also, let's do that one. Wait, hold on. Nafani, I think Nafani's right. Hold on, wait, Nafani, what did you say? Hold on, let me see your chat there. Nafani's absolutely right. X4 and x5, but then x3 is written in terms of x4 and x5 by the second equation. That means then x2 is the next one. Very good, Nafani. Very good. Okay, well then let us proceed on here. Let us proceed on. So now we can express the vector x as a linear combination of vectors u, v, and w. And so every linear combination of u, v, and w is an element in the null space. Thus, the vectors those vectors u, v, and w form a spanning set for the null space of A. All right. So one moment here. All right, are there any questions on that? All right, well, we're halfway there. Now we got to talk about, well, we've talked about the null space. Let me show you another space called, another subspace called a column space. Okay, now a column space, again, if you have a matrix A, the column space of A, called COL of A, is simply the span of the column vectors of the matrix A. That's how the column space of A is defined. It's the span of the column vectors A1, A2, A3, AN, up to AN of the matrix A. And since the span of a set of vectors is a subspace, that means the column space is going to be a subspace of Rm. Oh, why Rm? Now, why Rm? Why not R? Why in theorem 3? Why is the column space of a matrix A a subspace of m-dimensional space? Why not n-dimensional space? What's going on with that? Why would that be? Why would a column space of a matrix A in theorem 3 be a subspace of m-dimensional space? Good, Benjamin. The column vectors of the matrix A are of length m. The matrix A is an m by n matrix, so that means the column vectors have dimensions m by 1. Very good, very good. And so therefore, well, that's the reason why. All right, are there any questions so far? All right, so I'm giving you a guided tour. The textbook has very good examples, and just kind of having a discussion here. So formally then, the column space of A is the set of all vectors B such that B equals A times X for some X in Rn. But I'm more. I mean, that's fine. That's fine. But I think it'll feel better for you if we get to some examples. So let's get to some examples. So okay. All right. Find a matrix A such that W is the column space of A. So here's this space W, okay, and the space W lives in R3. Okay, well, all right. So what we can do is we can rewrite W as a linear combination of two vectors. Okay, so vectors that are in space W can be expressed as a linear combination of vectors 6, 1, -7 and -1, 1, 0. Well, okay, that means W is the span of two vectors. Okay, the span of two vectors, and so automatically we've shown that W is a subspace, and the spanning set would be the columns of that matrix A there. So the matrix A is as you see here, and W would be the column space of A, because the W is the span of the column vectors of the matrix A. All right, are there any questions on this? All right, I'm just looking here. Okay, we're fine. Let's continue on. Let's continue on here. Then, if we're good, let's continue on. All right. All right, I wanted to look at, yeah, this here, example 7. Okay, so I think that example you're going to be okay with. I want to stop and give you like 20 minutes here to work on section 7.2. I think you're going to be fine. So let me go ahead here. If we're good, I'll stop the recording. Are there any questions at all? All right. So.